Let's now get into cross products. Let C be the cross product of the vector A with the vector B. I'm telling you now that C will be perpendicular to A and it will be perpendicular to B. Suppose I have A here and I have B here, and let this angle between them be theta, so this is my plane of the paper is through the plane of the vector A and B. The direction of the cross product must be perpendicular to my paper then, because C is perpendicular to A and C is perpendicular to B, so C has to be perpendicular to both A and B. I have two choices now. Perpendicular to this paper could be either out of the paper or it could be into the paper. And now comes what I call the corkscrew rule. I always apply the corkscrew rule, and that is the following. You rotate A over the smallest angle to B. And if that's a counterclockwise rotation, then this vector C is coming towards me, perpendicular to the paper. A vector is an arrow, and this is the tip of the arrow, and I see the tip, so it's coming towards me. If, however, I had B cross A, then I have to rotate B, which is the one that is first mentioned, over the smallest angle to A. That now is a clockwise notation. And now this vector goes into the paper. Now, how do you remember this corkscrew rule? I think that's very simple, and this is the way I learned it in high school, and I always use it. There are other ways to determine the direction of a cross product, of course, but I prefer this one. I have here a corkscrew, and I have here a cork. And if I turn, as seen from this side, clockwise, then the screw goes into the cork. I go this way, clockwise from this direction, and it goes in there. Notice, when I go from B to A, I rotate my corkscrew clockwise, and the corkscrew goes in. Now, looking from this direction, I go counterclockwise. And what does happen? The corkscrew comes out again. So here, here I go from A to B, counterclockwise, and so the corkscrew comes towards me. I can do it with a potato, then you may be able to see it even better. Maybe we can see it from above even. If I, this angle. I turn clockwise, and you can see that the vector goes in there. I turn counterclockwise, and the vector comes out. I call this the corkscrew rule. You may not like this one, you may have a different method to find the direction. Be my guest. I always in my head apply the corkscrew rule. So it follows from what we just learned that A cross B equals minus B cross A. Because remember, if this is coming vertically out of the paper and this is going vertically into the paper, then They are 180 degrees apart. Very different situation we have with dot products, whereby A dot B is the same as B dot A. So now we know the direction of the cross product. We discussed that in detail. Now comes the question, what is the magnitude of the cross product? If we have a vector A and we have a vector B, then the magnitude of A cross B, this indicates magnitude, equals the magnitude of the vector A itself times the magnitude of the vector B itself times the sine of the angle theta. Now look at this a little bit more closely. If I made here a parallelogram, then I would claim that the magnitude of the cross product between A and B is this surface area. And you can easily see that this is length A, but this length is B times the sine of theta. If this angle is theta, this is also theta. And so the area B sine theta times A is this area, which is exactly the same as this area. So it follows immediately that if theta is 0 degrees or 180 degrees, that the cross product is 0. The dot product is 0 when theta is 90 degrees. Then we have the dot product equals 0. When theta equals 0 degrees or 180 degrees, then the cross product equals 0. Now comes the $64 question. We know the direction of a cross product. We know the magnitude of the cross product. And you may say now, well, it's all very nice and dandy, but if you give me two vectors in 3 dimensions, how can I find the vector notation of the new vector with all 3 components, x, y, and z? Well, I will give you an easy recipe for that, which is exactly consistent with what I told you, namely we discussed the direction and we discussed the magnitude. So what I'm going to tell you now is not new, but it's just a different representation of exactly the same thing. And I will show you that the two are consistent. If I have a vector A and a vector B, and A comes first and B comes second, so C equals A cross B, then I write down here some kind of a matrix. I write down X roof, Y roof, Z roof, A of X, A of Y, A of Z, B of X, B of Y, B of Z. But I repeat this here. Looks like a bit of hocus pocus, doesn't it? And I repeat this here. And I repeat this here. Magic, isn't it? And I repeat this here. Okay, be prepared now. Now comes the easy recipe for you to remember the 3 components of the vector C. And this is what I always use. I start here at the x, and I go to the right-hand corner. C of x, that's the x component, is the product of these two numbers, ay, bz, minus the product of these components, which is az times by. Now comes c of y. That's the product of these two components plus az times bx minus, and you guessed it, ax times bz. And the z component would be ax by minus ay bx. The vector c, of which this is the x component, this is the y component, and this is the c component, must be perpendicular to A, it must be perpendicular to B, and the magnitude of that vector must be the magnitude of A times the magnitude of B times the sine of the angle. It better be, because that is what I told you earlier, is what a cross product is all about. So let's look at that in some more detail. First of all, I can write down this vector c in a very elaborate way. You may not like that. I don't, but let's do it. C would then be a of y bz minus a of z by x roof plus a of z bx minus a of x bz y roof plus a of x by minus a of y bx z roof. So that's the vector in all its beautiful glory. Let's now take a vector A, and we take the one that we have worked with before, 3x roof minus 2y roof plus 4z roof, and we take B, which is one we have also seen before, minus x roof plus 3y roof plus 2 z roof. What now is C? Well, AYBZ. AY BZ. That's minus 4. Minus AZ BY. AZ BY is 12 with a minus sign. Minus 12 in the x direction. Plus, and you check the numbers that I'm going to write down now. You check them for yourself. You better do that, because I could make mistakes. So I find that the factor C equals minus 16 x roof minus 10 y roof plus 7 z roof. And now I want to check whether this vector, which is the cross product, meet all my previous conditions. It should be perpendicular to A, and it should be perpendicular to B, and it should have the right magnitude. How do we know whether C is perpendicular to A? Now our knowledge of dot products comes up. If we can demonstrate that the dot product between A and C is 0, their angle is 90 degrees. And that's relatively easy. Dot products are not so very hard. So let us see now whether indeed C dot A, or A dot C for that matter, whether that is indeed 0. It's a requirement. They must be perpendicular to each other if I have done it right. If I have calculated C correctly. Well, this equals Cx Ax plus Cy Ay plus Cz Az. And we know what A is, and we know what C is. And so when I plug in the numbers, I find minus 48 plus 20 plus 28 equals 0. Youppi! It is 0. Now I can ask myself the question, is C dot B also 0? It better be 0 because C has to be perpendicular to B as well. Well, when I work that out, I find 16 minus 30 plus 14, and that is also 0. Youppi! So I have shown you now that the vector that I found, A cross B, indeed is perpendicular to A and is perpendicular to B. Now comes the question, is the magnitude the right magnitude? Is the magnitude of C A, magnitude of A, times the magnitude of B, times the sine of theta? We know, of course, that the magnitude of C must be the square root of C of x squared plus C of y squared plus C of z squared. And that is easy to calculate. You know that Cx is minus 16, C of y is minus 10, and C of z is 7. When you work this out, you will find that this is approximately 20.1. It's the magnitude of the vector. What is this? Well, A, you remember, was the square root of 29. B is the square root of 14. And theta, as we calculated earlier for the combination AB, was 92.8 degrees. If I substitute that in here, what do I find? 20.1. So I feel very happy that you see that the two are identical. We found a vector in 3 dimensions using this recipe, which is rather complicated, and we indeed were able to demonstrate that that new vector, that cross product C, is indeed perpendicular to A, perpendicular to B, and it has the right magnitude. Which we did not check. It's one thing whether it has the right direction. You still have the direction in this direction and the opposite direction. Well, I will leave that up to you. But that's the one thing I have not demonstrated yet, that it has the right direction. You remember? The corkscrew rule gives you the right direction.